Now that we have derived the work done as integral PDV, we are going to apply this integral PDV to various thermodynamic processes. The various thermodynamic processes are constant volume process, constant pressure process, constant temperature process, adiabatic process, and polytropic process. So we are going to see how this integral PDV can give us various standard equations for the thermodynamic processes. So if I start with the first one, that is the isochoric process. Isochoric process is nothing but a constant volume process. If you look at this figure, you will understand. See, we have at state 1 a closed vessel being heated. So what happens? The gas, when it gets heated, will be expanding, trying to expanding, but as the vessel is having a constant volume, the volume or the expansion cannot happen, and thereby the pressure will be increasing. So when it reaches a state 2, you can see that the volume remain constant, but the pressure will be a much higher value, because as the gas cannot expand, it will actually increase the pressure in its own way. Now if I take a PV diagram, this can be represented by a constant volume, can be represented by a vertical line, say 1 to 2. So you can see that here V1 will be equal to V2. Now I'm going to find the work done during a constant volume process. We know that V1 is equal to V2, that is why this is called an isochoric process. Applying the work equation, W is equal to integral 1 to 2 PDV. You can see that the important term here is dV. dV is equal to V2 minus V1, because it's a process 1 to 2, process is from 1 to 2, V2 minus V1. So here you can see that V2 is equal to V1, therefore this value will be 0. Therefore, during a constant volume process, the integral PDV work is equal to 0. Now we will go to the isobaric process. Isobaric process is the one in which the pressure remains constant. If you look at this figure, again you can see there is a piston cylinder arrangement and a gas is enclosed here. When the gas is heated, what happens? The gas will be trying to expand, thereby increasing the volume, and if I try to contain that particular expansion process, then the pressure will be increasing. But what I'll do is I will be compensating the pressure by means of these weights. By removing or adding weights, I can maintain a constant pressure. So therefore, in this process, the volume changes from V initial to V final, or maybe from V1 to V2, and by the help of these masses, maintaining the mass, I can have a constant pressure out here. Now again I am taking a PV diagram, and this is a constant pressure process, the isobaric process. Constant pressure, that means P1 is equal to P2, that is why it is called an isobaric process. Now the isobaric process, I can draw it as a horizontal line, say 1 to 2. Now you can see that the volume is changing from V1 to V2, and we know that the area under this curve will definitely give us the work done from 1 to 2. Now I'll find it by using the equation W is equal to integral 1 to 2 PDV. So I'm applying this one. This is equal to P into integral 1 to 2 dV, as pressure P1 is equal to P2 is equal to P, which is a constant value here in isobaric process. Therefore, I can write this equation as W is equal to, what is 1 to 2 PdV? It is the range from 1 to 2, that can be written as P into V2 minus V1. So during isobaric process, the work done is equal to pressure, the constant pressure into V2 minus V1, and the unit can be joule or kilojoule here. And the work done under this curve 1 to 2 will give you the work done by the concept of area under the PV diagram.